Okay, finally got it started. Hope it continues. Right, what I want to do start with, there are lots of inequalities that one uses in analysis. So I would like to put in one place some of the standard inequalities so that we can keep referring to them whenever we want. Okay. And we do by some very famous quote somewhere I read that half the time an analyst spends time looking for some inequality which he wants to use. In the other half he spends trying to prove it himself. So because it is so many are there, many a times it's easier to prove it yourself than get it. But I am going to look at some very standard inequalities first, and so I'll put it in one place which we'll be using every now and then. So I'll call this as an inequalities section. There are many, so what I am going to do is look at some very simple inequalities. First I will concentrate, probably to start with, three inequalities. One is called the AM-GM inequality. The arithmetic mean, the geometric mean inequality. And the other one, the Cauchy-Schwarz inequality. And the third one is the triangle inequality. What we'll do is first we'll look at each. I'll take one by one. Look at the triangle. The first, for example, the AM-GM inequality. Look at that inequality in its simplest form, and then see how it gets slowly generalized, and in what form we get it as far as possible. We see how far we can generalize it. The first is the AM-GM inequality. The famous book by Hardy, Littlewood and Folliot, Inequalities, and that itself is considered very old-fashioned now. It's a huge book, but still there are a lot more that have come up after that. But that's extremely difficult to keep track of all of them. Okay, what does this say? This simply says the following. Suppose we have two numbers which are non-negative real numbers. A1 and A2 are non-negative real numbers. Then we'll use this notation. Whenever we have a set of numbers like this, organized, we have a sequence of numbers, we'll organize this as a vector. Okay? A equal to A1. Then the arithmetic mean, it's called the arithmetic mean of these two numbers is simply A1 plus A2 by 2. The usual average is the mean. And the geometric mean is simply square root of A1, A2. Right. whenever I say square root, see a1 and a2 are non-negative numbers, the product is non-negative, therefore there are two square roots. We always mean the non-negative square root. When we want to refer to negative square root, we will write minus square root of this. Okay? So the square root always stands for, by convention, the non-negative square root. Okay, with this, then we have the following. If we take the square root of a1 and the square root of a2, both are well defined because they are non-negative, and square it. The square of any real number is always non-negative. So 0 can be less, 0 has to be less than or equal to that. Now we expand this, so therefore 0 is less than or equal to a1 plus a2 minus 2 root a1 a2. Or you take it to this side, you get square root of a1 a2 is less than or equal to a1 plus a2 by 2, which is simply GA is less than or equal to. And that's what in the simplest form the arithmetic geometric mean inequality is. Okay. Now when will equality take place here? When equality takes place here? When equality takes place here? When equality takes place here? When root a1 equal to root a2, that is a1 equal to a2. So equal only a1. And that's what is the simplest arithmetic geometric meaning. So the AM-GM inequality in its simplest form is a1, a2 greater than or equal to 0 implies GA is less than or equal to AA, where that notation is used, and equal only a1 equal to a2. That is the first simple form of the AM-GM. Now we look for generalizations. We look for generalizations in several forms. Okay, the first one is, suppose instead of I have two numbers, I have n numbers. Okay. So now I look for a1, a2, an greater than or equal to 0, and then I define for a to be that vector a1, a2, an, just for shorthand notation. Then the arithmetic mean AA is the usual average, a1 plus a2 plus an by n, and the geometric mean now is, previously we had a one power which we equally distributed to the two numbers, a1 to the power of half, a2 to the power of half. Now we have one power, we have to distribute it to n numbers, so each one will take 1 by n power, so I will write it as a1, a2, a3, an to the power of 1 by n. Then question, GA. So similar geometric arithmetic mean inequality, does it hold for n numbers? And the answer is yes. And in fact equal if and only if all numbers are equal. In previous case all numbers had to be equal in order to get equality. Now all numbers have to be equal. Now there are many proofs of this. I am just going to indicate a simple induction proof, which is a clever proof by Cauchy himself. Okay? Extremely smart proof, and there is some moral in that. You will see that too. Okay? What Cauchy did was the following. This dyadic division. Suppose instead of two numbers I had four numbers. So you moved from 2 number result to 4 number result, and 4 number result to 8 number result, 16, 32, then you prove 2 to the n in general by induction. If it is true for 2 to the n minus 1, it must be true for 2 to the n. So it took care of all the dyadic powers, that many numbers. Then if it was not dyadic, It was somewhere between two dyadics. He supplemented enough numbers to make a dyadic and then took it. It was a smart overcoming the shortfall. And essentially that's what the fast Fourier transform fellows did. See, they keep on bisecting, dividing into 2 by 2 by 2 by groups, and finally they came to a plus b and a minus b. Nothing else was there. So this idea of dividing them by dyadic divisions is, so let us look at the 4 case, okay, just for illustration. Okay, let me do the following. Let me write the 4 case and then keep a gap, and then we'll see what happens in the n case. So let us first of all look at 4 numbers. So I have A1, A2, A3, A4 greater than or equal to 0. A is my vector A1, A2, A3, A4, and AA is A1 plus A2 plus A3 plus A4 by 4, and GA is A1, A2, A3, A4 to the power of 1 over 4. Okay? Now, you divide these 4 numbers into 2 groups. The first 2 in 1. Right. What is the clever way and the way that you do in FFT is take all the evens and the odds, and in the evens all the evens, in the odds again the evens. You go on doing that. So it's not necessary, that much cleverness is not needed here. Just take x to be A1, A2 and y to be A3, A4. Okay, just divide it into 2 groups of 2 numbers. Now look at this vector and apply AM-GM inequality for AX and GX. For 2 numbers we are valid, so we have GX is less than or equal to AX. Similarly, GY is less than or equal to AX. Then the cleverness even in the FFT is, after dividing them, putting them back together. Now put them back together. What you do is you define a new number called alpha, which is AX. Okay. The average of the average. Now we are looking at the averages of the 2 averages. That's all. Okay. And what do we get? G alpha less than or equal to A alpha. Because again we are looking at only 2 numbers. The geometric arithmetic inequality is valid for 2 numbers always. Now we are looking at 2 number case for 3 different situations. One A1, A2, A3, A4, and then AX, AY. Now what happens? Now I am going to leave some space here. I am going to write for the general case there exactly what happens. And then continue. Now first of all, what is A alpha? If you look at A alpha, it is nothing but x, what is that? AX plus AY by 2. This is the average of these AXs and the AYs. But what is AX plus AY by 2? A1 plus A2 by 2 plus A3 plus A4 by 2 by 2. So it simply becomes A1 plus A2 plus A3 plus A4 by 4, which is AA. So if I call this as 1, what happens to 1? G alpha is less than. Now if I somehow show GA is less than or equal to G alpha, I am finished. GA is less than or equal to. Right. Now look at these 2 equations, GX and GY. What does that tell us? GX times GY is less than or equal to AX times AY. That is from these 2. So the square root is less than or equal to square root. But that's precisely what? GA. So substitute here Therefore, you get square root of gx gy is less than or equal to g alpha, which is less than or equal to g. Now only it's just identifying that is exactly equal to g. Okay, but this is exactly equal to g because this is square root of gx is square root of a1 a2, gy is square root of a3 a4, and therefore 1/4 power will come. So GA. That's the simple fact that dividing by two groups you can achieve it for 4 numbers. Now when you are given 8 numbers, you divide it by 4 groups and then apply the result for the 4 groups to get the 8 group result, and then you go on like that. So in general, suppose you had n equal to 2 to the power of n numbers, a1, a2, an, and the result is true for, if the result is true for 2 to the n minus 1 numbers, that is the induction hypothesis. We already verified that it is true for 2 squared. Now suppose it is true for 2 to the n minus 1, how do you go to the 2 to the n case? Follow this procedure. Let's call n as n by 2, which is 2 to the n minus 1. So it is true for L numbers. Okay. So now if I divide it into 2 groups of L numbers, so simply follow this procedure. X to be equal to A1, A2 up to AL, Y to be AL plus 1, etc. AN. And then just the same thing, dx will be less than or equal to ax. Why? Because we assume the result is true for L numbers, and similarly gy will be less than or equal to ay, and you define a new number alpha equal to ax comma ay, and you get this result. This result is true because the inequality is true for 2 numbers. Now simply they get carried away. You get A alpha is exactly equal to AA, and this inequality becomes therefore G alpha less than or equal to AA, and this result gives me square root of Gx Gy is less than or equal to G alpha. Exactly same steps will come, and you get square root of Gx Gy is less than or equal to G alpha less than or equal to AA, and this is this. So there is no difference in the proofs. If you do carefully, exactly same thing, all the steps mimic themselves, repeat themselves, and you get the result. So therefore, you have the arithmetic geometric mean inequality for whenever the total number of numbers involved is a power of 2. What do you do when it is general? Okay. The last case is therefore, suppose I will just write the, suppose we have n numbers where n is not.
So trying to prove it from I to I plus 1 is not easy.
No. It's not that easy.
It's not possible.
Why I like this proof was cute. A very clever proof. And this idea comes in several places. That's why I like this proof. There are many proofs. Okay, you can do a calculus proof, you can do some other proof, etc. etc. You can even give a probability theory proof.
Right.
It's a very interesting proof, probability proof that there are infinite number of prime numbers. You know very easily a simple proof by Euclid, but there are probabilistic. For the same thing, there will be several proofs. There are, this being very oldest inequality. There must be umpteen number of proofs. Okay. What I liked about it was the ideas involved in it. So then what you do is, whenever something is not a power of 2, particularly present day binary thinking, so this is the how even Cauchy was thinking binary long back. if it's n is not a power of 2, it must lie between two powers. So n must be between some 2 to the n and 2 to the 2 to the n minus 1. So what the idea? The idea is, I had only A1, A2, An. My A was A1, A2, A. Instead of working with it, I will work only with powers of 2. So what I will do is I am going to supply more numbers and look at a bigger set. So what I do is when I supply numbers, I make sure I don't destroy the average. At least one of the averages. I don't destroy it. I easy not to destroy the arithmetic average. How do I not destroy the arithmetic average? If my run rate is 6 per first 30 overs, even the next 20 overs, in each over I score 6 runs. My average is still 6. So what I do is, whatever was this average, I supply it. Okay. So I am going to look at x, which is A1, A2, An. Then I am going to just supply AA. How many of them? Until I reach 2 to the n. So this will be 2 to the n minus. So this is An plus 1, this is An plus 2, etc. So all those numbers I supply to be the same constant. Therefore, if I take the new average, what is it? It is same as the old average. So Ax equal to Aa. Now we know that Gx is less than or equal to, and we want to prove that Gx is less than or equal to Ax. Why? Now because we are at the 2 to the power of n, but this is equal to Aa. Now play with this and see what is this. And then adjust terms on both sides, cancel some things and add some things, then you will get the Ga is less than or equal to A. So that's the, this is pi I equal to 1 to 2 to the n Ai to the power of 1 over
2 to the 2 power
over 2 to the n. Now split the terms where the things are all same and then the remaining, and then cancel things, we will get the right answer. Okay? The fellows who are all common will have a AA power, and that has to be adjusted with this AA power, and then that will neatly give Ga is less than or equal to A. That's all. That's the trick. Right. So that's the first breakthrough. We have now therefore the geometry. Now I can write the AM-GM inequality as A1, A2, An greater than or equal to 0, A equal to A1, A2, An, AA equal to A1 plus A2 plus An by n, Ga equal to A1, A2, etc. An to the power of 1 over n, then Ga is less than. And of course in all these things you can trace back and say the equality holds if and only if all numbers are equal. The same arguments will each step. In each one of these equality has to meet there, and everywhere you go on putting all numbers equal, and equal holds if and only if A1 A2. Of course the inequality is trivial if one of the numbers is 0, because the left hand side will become 0. That's not the big deal. So we can as well, without loss of generality, assume all the numbers to be non-negative. Okay. So now, further generalizations, more generalizations. So now we go to more generalizations. All these generalizations. Now, if you look at what we have done here, we have taken the average of these n numbers. When we took the average, we gave the equal weightage to all the fellows. Suppose we redistribute the weightage. Certain fellows are more important, certain parameters have more important contributions and then certain other parameters. Then we will define a weighted average. So suppose I have A1, A2, etc., AN, n non-negative n numbers, and I will call it as A equal to A1, A2, and lambda equal to lambda 1, lambda 2, lambda n, such that the lambdas are all between 0 and 1 and they add up to 1. It's like a probability distribution. Okay, discrete probability distribution. So then we define the weighted arithmetic mean A. It depends on for these numbers with the weightage vector as lambda. I define it to be simply summation lambda I A. And the weighted geometric mean to be, now A1 is raised to the power of lambda 1, A2 is that another guy, the power is also distributed according to the weight, A1, lambda 1, etc. So I can write it as pi I equal to 1 to Ki lambda. That's the generalized weighted arithmetic mean and geometry. Question, does the geometric mean inequality hold still? Question, is GA less than? And of course, equality if and only if all the numbers are this sort of thing. Now, the answer is this. We will see why. I mean, we'll just look at this question. So, what we are looking for is, we want to know if phi I equal to 1 to n ai to the lambda I is less than or equal to summation I equal to 1 lambda I. This is what we want to know, whether this is true or false. Now, this is true, this holds if and only if suppose I take logarithms on both sides. What happens? If a number x is less than or equal to y, then log x will be less than or equal to log y, and conversely if log x is less than or equal to log y, x will be less than or equal to y because log is a monotone function. Okay. So, since log is a monotone function, holds since log is a monotone, non-decreasing, increasing. So this will hold if and only if this holds. Okay. This will hold if and only if logarithm of a product is the sum of the logarithms. So it will be sum of log ai power lambda I, but log ai power lambda is lambda I. So this will be sum I equal to 1 to n lambda I log a less than or equal to log summation I equal to. So we are asking, therefore, we are asking if log lambda ai from I equal to 1 to n less than or equal to log I equal to 1 to n lambda I. Right? This is what we are asking. Now, suppose for a moment I said, why do I use log? I could have chosen any monotone function. The same answer would have been asked. Isn't it? Instead of the logarithm monotone increasing function, I could have taken any monotone increasing function phi and said that this holds if and only if lambda I phi. So, similarly, what do you mean? Any question?
The power won't come as a product if you don't take.
That won't come. So therefore what, I know that. That's why I am going to put this question, what I am going to write. Similarly, at this stage, if we replace log by some other function phi, which has reasonably common properties, whatever that means, I don't know, common properties with log, then ask if I equal to 1 to n lambda I phi ai less than or equal to phi summation I equal to 1 to n lambda. In other words, what I am saying is, suppose I tell you whenever a function phi satisfies these conditions, then this inequality is true, I will go and verify whether log satisfies that condition. And if log satisfies that condition, I have that list. Okay. So what I am really asking is, for what type of functions will such an inequality hold, and is log one such function? If log is one such function, then that inequality. If log is not one such, well, okay, then we get that inequality. And this itself becomes a further generalization of the arithmetic-geometric mean inequality. If lambda i's are like this, and phi is such a function for these holds, this is another form of the arithmetic mean geometric mean inequality, which is looking differently. And this is essentially what leads to the convexity arguments. Okay, so we will make a statement. Now, this leads us to the notion of convex function. I will just discuss it in the minimal level. I will not get the most general form of this, even abstract vector space and things like that. What do we mean by this? So, we say, suppose I is an interval in R. I will just restrict myself to functions of one variable defined on an interval, okay? I won't take a convex set in the vector space, etc., etc. Make it more general, but let's stick to this parameter. We say is a convex function if I will write many things. Strictly convex function, concave function, and strictly concave function. If equal convex function, if phi of lambda a 1 plus 1 minus lambda a 2 is less than or equal to lambda phi a 1 plus 1 minus lambda phi a. Of course, a1, a2 were belonging to I, and 0 less than to lambda 1 less than equal to 1 lambda. the convex combination, the other one is, total sum must be 1, lambda 1 and lambda 2. So one of them is lambda, other one must be 1 minus lambda. And I will say it is strictly convex if it is convex and equality holds if and only if A1 equal to A2. Concave with minus pi is convex, which means the inequality gets flipped around. That is lambda pi A1 plus 1 minus lambda pi A2 is less than or equal to pi of lambda A1 plus 1 minus lambda. And again strictly concave if phi is concave and equality holds if or only A1. So now if you look at this, suppose we had only two numbers, A1 and A2, then lambda 2 must be 1 minus lambda 1 because sum is 1. So what we are asking for is concavity. What we are asking for is concavity, and we want equality if and only if holds, then we are asking for strict concavity. So if phi is a strictly concave function, this result holds. Okay? For at least the generalized arithmetic geometric mean holds, weighted arithmetic geometric mean holds for two numbers. That's all we know so far. Nothing more than that. So we reduce the size again back to two numbers, but we generalize to a weighted arithmetic geometric mean. Okay. Right. So therefore, we get first step, if phi is strictly concave, A1, A2 greater than or equal to 0, 0 less than equal to lambda less than equal to 1, 0 less than equal to lambda 2 less than equal to 1, lambda 1 plus lambda 2 equal to 1 implies lambda 1 phi A1 plus 1 minus lambda 2 phi A2 is less than or equal to phi lambda 1 A1 plus lambda 2 A2 for every A1 A2 concave in I. Okay, all this. And now how do I decide whether a function is convex or concave? Well, it's hard. You have to look at the graph, you have to look at inequalities. You may have to come back to this definition itself. So you may be cheating, saying that I have got the inequality, but that inequality itself is the definition, and so on and so forth. But if the function, if you are looking for very smooth function, then we can make some statements. If phi is differentiable twice, then we would have phi double prime to be less than or equal to 0 for concavity and strictly less than 0 for strict concavity. Okay. So, if these are things which we will prove later when we deal functions, but this is only when we discuss continuous functions, etc., differentiability. We will come back to these geometric ideas, but right now we will simply take that result. If phi is twice differentiable, then phi is strictly concave, phi is concave if phi double prime x is less than 0 for every x in I, and strictly concave if phi double prime x less than 0. Concave less than or equal to 0, strictly concave. What this means is the derivative must be a decreasing function, or it should be non-increasing function. Here the derivative must be strictly decreasing function. The derivative of the derivative is less than 0 means the function is decreasing. Rate of increase is negative. That means it is dropping. So rate of increase of the rate of increase. Therefore, this is the rate of increase of the velocity or the slope. or the change of the function, that must be negative. So the derivative must be a non-increasing function for concavity and strictly decreasing function for strict concavity. Is that okay? Now, if we let phi x equal to log x and I to be 0 infinity. It's nice, continuous. Phi prime x is 1 by x and phi double prime x is minus 1 by x squared, is strictly less than 0. This, and therefore log x is strictly convex, strictly concave. In 0. And therefore I can apply this result for any A1, A2. I should not have written what? What should I have written here? A1, A2 in I. Because if it is not in that I don't even know what phi A1. Whenever I refer to the domain or definition of the concavity. Now if we take phi, it is strictly concave, so I want to take A1 and A2 to be in the domain or definition of I, which means non-negative real numbers. So if I take two non-negative real numbers and I write this, I get the weighted arithmetic geometric mean for two numbers. Therefore, hence lambda 1 phi A1 plus lambda 2 phi A2 or log A1, alright, log A2 is less than log lambda 1 plus lambda 2 A2 A1 A2 greater than 0. Now why do I write greater than 0? Because it's not there. But then I don't worry about equal to 0 case because it is a trivial case because the left hand side becomes 0. The geometric mean becomes 0. So, and this implies A1 to the 4 lambda 1, A2 to the 4 A1. So that is the arithmetic geometric mean, weighted arithmetic geometric mean for two numbers. Now how do I do for n numbers? It's always some kind of a induction will have to be done. Okay. So the induction will have to start somewhere here. From the definition, in the definition of concavity or convexity, we involve two numbers. Now we have to say that concavity or convexity pushes that definition for n numbers also and their combination. Okay. And that is what is known as the Jensen's inequality. We proved it exactly 100 years ago. I think it's a centenary of Jensen's inequality. It is a 1906 paper. So, that is the next case, Jensen's inequality. Now, if you prove for one of these concave or convex, the other one can be got by putting minus. So let's say it is okay. Let's say phi is convex. Alright. Integral I. Then A1, A2, AN belongs to I. Lambda equal to lambda 1, lambda 2, lambda n. As before, 0, this is the probability distribution, summation lambda n 1. Then, phi summation I equal to 1 to n lambda I ai is less than or equal to summation I equal to 1 to n lambda I. The inequality is shifted backwards if it is concave. That's all. We are looking for that concave business. Now this, we know if only two of them were there, that is precisely definition. Okay. And for one there is nothing to prove. The geometric mean and arithmetic mean all are that number itself. So there is really nothing to weighted, mean, ordinary mean, any mean, they are all the same. So we know only one thing. So n equal to 1, trivial. N equal to 2 is definition of convexity. So basically, therefore, we are asking for n which okay. Whether that is true for it. Suppose true for n minus 1 numbers. What does that mean? Phi, which way is phi summation I equal to 1 to n minus 1 lambda I ai is less than or equal to summation I equal to 1 to n lambda I phi ai. Suppose this is true for n number, n minus 1 number. Now what do I have about lambda 1, lambda 2, lambda 3, lambda n minus 1? That sum must be equal to 1. But now I want to prove for n numbers. Now look at n numbers, a1, a2, etc., an, and lambda 1, lambda 2, lambda n. Now their sum of these n numbers is, it's not that lambda 1 plus lambda 2 plus lambda n minus in 1 and then I am adding a new number. So this, so what I am going to do is, so let me write it this way. Okay, so let's take instead of lambda I there mu I, because I want to use lambda I here. So whenever you have a convex combination, that such a combination is called convex combination. Okay. Whenever you have a convex combination of n minus 1 numbers, this inequality is set. So you can generalize it further. Instead of taking these numbers in an interval, you can take a vector space and take these vectors and then look at the subspace generated by them, and then take a linear combination of these vectors and look at the convexity of a function defined on a subspace. And even if you don't want subspace, you want only, whenever you have such n numbers, any convex combination must also be there, and that is called a convex subset in a vector space, and you can do all that generalization. But let's look at this ground state level right now. Okay. Now suppose I look at n numbers, and summation I equal to 1 to n lambda I. Now, so I have lambda summation I equal to 1 to n lambda I is 1. So I will write it as summation I equal to 1 to n minus 1 lambda I plus lambda I equal to n equal to 1. So I want to bring to that n minus 1k. How do I do the induction? Somehow I want to bring it to the problem of n minus 1 situation. And therefore, summation I equal to 1 to n lambda I is equal to 1 minus lambda n. So if I divide by 1 minus lambda n, I get summation I equal to 1 to n lambda by 1 minus lambda n is 1. So I will call this as mu I. And you may say, what is lambda n equal to 1?
n minus 1.
Where? Oh yes. What if lambda n equal to 1? Then there is no problem. All the others are 0. Okay. So that without loss of generality, lambda n is not equal to 1. Right. So now I have this mu1, mu2, mu n minus 1. All are less than 1. Okay. Because already lambda I, why are they less than 1? Total sum is 1. Okay. They are all non-negative. They cannot be exceeding 1. Now, what can I say therefore? I equal to 1 to n minus 1 mu I ai phi of this will be less than or equal to right, because we assume that the result is true for n minus 1 numbers. Now our problem is, look at this. This is okay. We want to look at this. That was our original problem. Now what I am going to write it here is this. I write as pi summation I equal to 1 to n minus 1 lambda I ai plus lambda n. Okay. This I can write as phi. What is lambda I? Lambda I is 1 minus lambda n times mu I. I call this as mu I. So lambda I is 1 minus lambda n times mu I. So I will write it as mu I ai. 1 minus lambda n is common. Again there is an n minus 1 plus lambda n. Right? Now you look at this number as x, this number as y. What have I got? Two numbers, convex combination, because I got now lambda n and 1 minus lambda n. The sum is 1. So first apply the definition of convexity. So this is less than or equal to 1 minus lambda n times phi summation I equal to 1 to n minus 1 mu I ai. This is this into phi of x plus lambda n into phi. The rest of it is history, because now I can put that thing there. This is less than or equal to 1 minus lambda n into summation I equal to 1 to n mu I phi ai plus lambda n. Why is n? And 1 minus lambda n times mu I is lambda I, back to my lambda I. So this is equal to summation I equal to 1 to n minus 1 lambda I phi ai plus lambda n phi ai, which is the same as summation I equal to 1 to n lambda I. This is again the same trick. You divide it by two parts and then apply the two result which is available for you and apply the n minus 1 result. Together you combine, you get the result for the general integration. So therefore, Jensen's inequality says for convex functions this is true, and again we can show that equality businesses etc. So we will hold that, we will take it for granted. And then if the right equality holds, if it is strictly convex, equality holds if and only if all these numbers are equal. Okay. Now, therefore for strictly therefore if I have concave, what is the corresponding result? Summation lambda I phi ai is less than or equal to phi summation I equal to 1 to n lambda I. Now phi is equal to log x. Is concave, strictly concave, and therefore summation lambda I phi ai equal to 1 to n log ai is less than or equal to log summation I equal to 1 to n lambda ai, and take antilogs, you got ai and I phi is less than or equal to summation ai, which is just e. Results, this go on generalizing. All you had was that she started with the fact that the square of a real number is non-negative. Then he applied it to root a minus root b, and then got it for a plus b by 2 and square root of ab. And then said I will split that weight equally, and then I got a1 plus a2 plus an by n. Then I got little bit bold and said, why do I split it equally? I split it arbitrarily as long as I distribute that 1 rupee in 10 paisa to somebody, 8 paisa to somebody, 22 paisa to somebody. And still the arithmetic mean geometric mean is. So in other words, what saying is, you may have a class, the same mark may be scored by 8 fellows, another mark scored by 12 fellows, another mark scored by 13 fellows. How do you calculate the mean? You calculate the weighted mean. The mean is distributed 8 by 57, 13 by 57, and the number of students in the class 57. So the weighted mean is also, you can have as long as, the weighted mean is always a convex combination. So this is how originally we started preparing frequency tables and then calculated the averages, etc., etc. in high school we are taught. That sort of thing is what we are doing. Many times, I think many of these inequalities from a statistical point of view also, this fellow has developed a lot of, I think many of these convexity arguments also. One from the mathematics side, one from the statistician side. A lot of such inequalities come into picture. So therefore, we have a fairly general inequality, the geometric mean, arithmetic mean inequality for weighted means also. Now there are many more generalizations of this.
So that is true even for the infinite.
There you have to be very careful. Convergence, etc. See, the very question of convergence itself. What do you divide it by? You have an infinite convex combination. I don't know whether series converges. So therefore, you have to put in that it is a complete and all these things, and look at it as a limit. If you put the right conditions, the right things will happen.
But in a probability course, it is said that it's true in general.
Yes, you can do that. That's what there you have to put the right condition about convergence.
It converges.
Yeah, those things are needed. Okay, right. We will come back to again later when we come to LP mean and all. There we are going to add function, a continuum itself. We will be doing. Okay. This is the beginning. Okay, this is just the beginning. Okay. Now there are more generalizations of this. The story doesn't end here. You know, people eventually the way when somebody writes an inequality, quite a few of these inequalities can be recognized as their original DNA in that x squared is greater than or equal to 0 when x is real. Complex animals have grown out of it. See, for example, here itself we looked at this case through the logarithm, right? So, if I suppose I look at phi of x as logarithm of x, okay, then in the arithmetic geometric mean inequality with the weight, let's look at this left hand side. It is pi ai to the power of left hand, which we can think of as the inverse function of the logarithm of summation right? Because if I have what should I put correctly? A to the power of lambda I. Let me write it first. I can write, I wanted to get this as, how did I get it? I thought of it as logarithm of ai, lambda I, and then I took the anti-log, right? So I can think of it as phi inverse of this garbage where phi am. Okay? I can think of it as phi inverse of summation lambda I phi am. So instead of this, I look at a general monotone function for which inverse can be defined. Whenever you have monotone function, for every x, you have a corresponding y. You can define the inverse function for every y. You can define a corresponding x because it is monotone. Monotone increasing function or monotone decreasing function strictly. Then you can always define an inverse function. So, this is one such. I will call, whenever such a function, I will call it as m phi. A new mean. This is a new mean of these a1, a2, a3, etc. Okay? So how do I define now? Suppose I have a monotone increasing function phi, then m phi of A is simply phi inverse of summation lambda I phi ai. Now if you look at the right hand side, it is simply take phi t to be the identity function. Then it is simply what? Phi inverse of summation lambda I phi a. Right? Because it's just the identity function, its inverse is also identity. This is lambda I ai. Inverse of the identity function is also that. So this is just, so I can write this as, I will call it psi inverse psi ai, where psi t is the identity function. So this becomes m psi. So the geometric arithmetic inequality is simply something, if I have two monotone functions, one which is logarithm, the other one is the identity function, and I have calculated the mean with respect to the logarithmic function m phi, and I have calculated the mean with respect to the other function, namely the identity function, and I got m phi a is less than or equal to m psi a. That's all I have got. For when phi was log t, phi was log t log x, and psi was x. The identity. Now of course one can ask following question: what pairs of monotone increasing function m phi a will be less than or equal to m psi a? That's even further generalization of the arithmetic mean geometry. So we may think that arithmetic mean geometric mean ends with Olympiad program. It doesn't. It's only the beginning. And that's why some of those guys who go through this Olympiad program realize perhaps the power of this arithmetic geometric mean inequality, because its essence pulled up and up. It takes you quite far. Okay? And this leads to more and more about monotone function. You have a class of all monotone increasing functions. Then in this, you find all those pairs phi psi for which this inequality holds. M phi a is less than or equal to m psi a for a1, a2, an. Given a1, a2, an. Even that you can ask. Given a1, a2, an. Or is it true for all a? All kinds of variations of these questions you can look. And there are any number of results like this. I am not going to go into this. So what I am therefore saying is, there are lots of ramifications of this very simple arithmetic mean and geometric mean inequality. Now, that is the first thing that I wanted to discuss. But actually, I wanted to finish all the inequalities today, but I could not. Now, of course, the next with the simple, I will just write this in the simple form, the Cauchy-Schwarz inequality. Very more interesting things about AM-GM. This is very simple, everybody knows. Suppose I have a vector with two components belonging to R2 or C2, one is another vector, then you define the length of the vector to be the square root of x1 square plus x2 square, and the length of the vector y to be square root of y1 square plus y2 square. As I said always, whenever I take square root, I mean the non-negative square root. And we had in vector analysis, whatever name they give, some people call it vector algebra, vector analysis, vector calculus, people are highly confused. Okay. That I asked somebody, what have we studied? Some people will say vector algebra, some people say vector calculus, some people say vector analysis. It shows there is a confusion between algebra, calculus and analysis. Not about vectors. What is algebra, what is calculus, what is analysis? We are taught in the whatever vector blah 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 course, we are taught that this is geometrically this is equal to cos the angle between x and y. This is one of the things that we are taught, and from this it follows that mod x dot y, the dot product, is equal to mod x, the length of x, and the length of y, times the modulus of cos theta xy, and every child knows that cos theta lies between -1 and 1, therefore mod cos theta can be at most 1, and therefore this is true. Okay? And equality holds if and only if mod cos theta is 1, which means cos theta is plus or minus 1. That means theta is 0 or pi. That means the two vectors are in the same direction or in the opposite direction, but most importantly they are along the same line, and therefore they are linearly dependent. The two vectors will have to be linearly dependent. The equality holds if and only if that linearly dependent. That is the, we look at this inequality still, again back. Now look for generalization. The first generalization will be, I will just mention this in 2-3 minutes to conclude. The first generalization is instead of two components, take n components. That's like arithmetic-geometric mean we have two numbers, then generalize it to n numbers. Then if we have n numbers, and instead of real you can take them to be even complex, then define the length of x to be square root of mod x1 squared plus mod x2 squared plus etc. plus mod xn squared. The mod I have to put because of the complex number business, but similarly norm y, the length of y will be square root of mod y squared plus etc. plus mod yn squared. Then, I have to define x dot y to be x1 y1 bar plus x and yn bar. Again, this is necessitated by the complex business. Then the question is mod x dot y less than or equal to the length of x and the length of y equal if only x and y are dependent. And the answer is yes. We'll look at the proof of all these things. These are some of the most fundamental inequalities in mathematics. This is one of the most repeatedly used inequalities. And the next generalization is to push your luck, as he says, to infinite case. Okay. So suppose I have x1, x2, etc., xn, etc. Instead of finite number of components, you have infinite number of components, xi belonging to C. Then I have to define the length of x to be the square root of summation I equal to 1 to infinity mod xi squared. But then I run into difficulty How do I know the series converges? And therefore I will take only those vectors x. What do you do if you look at a basket of tomatoes and want to buy a kg, something not good, you throw it off. You don't know what to do with it. You don't know how to use that to cook. And so here I don't know what to do when it doesn't convert. I simply close my eyes and ignore its existence and take only those fellows who are convergent. Then I can define this. Then I define this. Once again, there is even a fundamental question of convergence of this series itself, the series of complex numbers. And it turns out that if I take x and y of the same type, this will also be true, and this will be true, and this will be true if another x and y. That is the Cauchy-Schwarz inequality in the general sense. Then we push our leg further. He was asking how far can we push this leg in the infinite case. Then what we do is, instead of taking just a discrete set of components, suppose I take a continuum of components. So now instead of this I consider x of t, where t belongs to some interval in the real life, equal to or also, doesn't matter, some interval of the real life, and xt is complex, so complex valued, so that is complex valued function of a real variable, and real variable varies over some interval which can be r or something like that. Then I have to define the square root of, here I took the sum of all the components, now I have to take the sum of all the values, and there I added, so I have to integrate. Now what does this mean? Does this integral make sense? So I will take only those functions for which this all makes sense, that's all, and this is finite. Okay? So I take only all those functions for which this makes sense and it is finite, and then define it to be that, and then x dot y is defined as integral over I, take the component of the first one, take the component of the second one with the conjugate, add them all, and that's what the equation. And whether that makes sense, well, whenever that makes sense, when you take carefully choose vectors like this will also make sense, and x dot y will be less than or equal to, or makes. And this is the Cauchy-Schwarz inequality in the so-called Lebesgue spaces, and Lebesgue L2 space, and this is called the L2 I space, and this is called the L2 N space. And equality if and only if xt and yt are linearly dependent. What does that mean? One of them must be a multiple of the other. Why did I say each must be a multiple of the other? It is possible that one of them is 0. Then only the 0 fellow is a multiple of this and that fellow is not a multiple of this. So one of them, at least one of them must be a multiple of the other. That's what is meant by linearly dependent. So we can push our luck phenomenally and we can go further and further. But then, okay, that's as far as the Cauchy-Schwarz, the second. No. So therefore I look at all these things next time. This Cauchy-Schwarz inequality, start from this to then show for n, from n how we move to infinite number, and that requires more work because we have to define integral, that will take a longer time. So we will wait till integration is defined and then do these things at the integral level. And we will hold that part later, but that results are all true correspondingly. Then comes the triangular inequality, and its generalization of the end will get something called Minkowski's inequality, and there are generalization of the Schwarz called the Holder's inequality. All that we will look at. So these are some of the standard inequalities. Arithmetic-geometric mean Cauchy-Schwarz, Holder's, and Minkowski's in its various forms, discrete, continuum, etc., etc. These are very fundamental inequalities to do analysis. I'll stop here.